Hello, I am Erdogan Madenci from University of Arizona. Thank you for your interest in this presentation. I'm going to talk about fatigue life and crack path prediction based on peridynamics and kinetic theory of fracture. So here's the outline. I'm going to briefly go over motivation, objectives, describe bond-based peridynamics, peridynamic element, how we couple peridynamics with finite element and ANSYS framework, and briefly describe kinetic theory of fracture, and then show you some numerical results and my presentation with remarks. So accurate prediction of fatigue failure is extremely important in order to enhance reliability and longevity of critical components. And these components are subjected to complex loading conditions. They have complex geometry. We may have multi-axial loads of different amplitudes and frequencies. And research continues in this area for more accurate assessment of fatigue life prediction. So the challenges in fatigue life analysis is because the long duration of constant amplitude and variable amplitude load spectrums we have, and including the effect of each cycle of the load spectrum, is computationally intractable. So therefore we end up with some simplifying modeling assumptions. They're either empirical in nature or based on stress, strain energy, strain, and related to fraction mechanics type concepts. So our objective in this study is to come up with a new fatigue life prediction approach in a finite element framework. So we will use kinetic theory of fracture, we'll use peridynamic theory, and we're going to couple peridynamics and finite element analysis in ANSYS. So bond-based peridynamics was introduced by Zhang in the year 2000. It's a non-local approach. It's a continuum approach. It basically replaces the divergence of the stress tensor with this integral that you see here. The integrand is f, which is known as force density vector, and the domain of integration, hx, is the domain of interaction, which also specifies the horizon of a point x. Now, on this figure here, point x will be interacting with other material points, x prime, within a finite distance, within its domain of interaction. This region is defined by the radius of that is delta. We refer to that as the horizon of point x. And as deformation takes place, so x becomes y, x prime becomes y prime, the displacement of x is u, and x prime is u prime. So also what I want to point out is that as this horizon approaches zero, delta becomes zero, approaches zero, then the non-local theory, this peridynamic theory, recovers the local theory. Basically, this integral that you see here approaches divergence of the stress tensor. And the integrand here is free of any numerical differentiation, so it's always valid regardless of the presence of cracks, for example. Now, in the case of this point x could be symmetrically located in the domain of interaction. If that's the case, we call it a symmetric horizon. And force density vector is expressed in terms of a bond constant c, this matrix S, which I will show you here later how we define that. And then the stretch, basically u prime minus u divided by the relative position between x and x prime. And for plane stress conditions, bond constant is given in terms of the Young's modulus and the horizon. And Poisson's ratio is a fixed value of 1/3. Okay. So this matrix S is expressed in terms of peridynamic functions. This G, matrix G, is expressed in terms of peridynamic functions and based on the peridynamic differential operator. And so basically these peridynamic functions only involve the geometric position of x with respect to x prime. Okay. So, and there's no need for surface corrections that you are normally familiar with in bond-based peridynamics. So if you have a non-symmetric horizon, basically if you are looking at x and x prime, so you have function s of xi, that's the relative position vector. And if you're basically on x prime, then you will be the negative of that relative position vector xi. So we basically define S bar as the average of these two. So for a non-symmetric horizon, force density vector is expressed in terms of bond constant, matrix S bar, and the stretch basically between these 2 points. Okay. And now the peridynamic element is very straightforward. So I'm looking at now the discrete form. So here you have point K and point J. So if you sum up all of these forces, Fkj, you're going to end up with the internal force vector, which is Lk. And I already showed you the definition of force density vector between K and J. It involves S bar and the bond constant. So I can write down the strain energy at point K in this particular form here. And if I apply Castigliano's theorem, I can determine the forces, the components of the internal force vector at point K and J as shown here. And if I rewrite this, I end up with the expression for the stiffness matrix between K and J. And specifically, I can write down or evaluate the stiffness matrix in terms of the coefficients of this S bar matrix that I showed you in the previous slide. And specifically, Sij bar are given in terms of these peridynamic functions derived based on the peridynamic differential operator. This parameter mu is a status parameter. If the bond is intact, unbroken, it has a value of 1. If it's broken, it has a value of 0. And so the peridynamic elements and their connectivity at node K are shown here. So for example, this red node K will be interacting with all of these points in its family member. The number of family members is n sub K. So we implement everything into ANSYS through the use of matrix 27 elements. Basically for two-dimensional analysis, we have UX, UI components associated with this node here. And the other node, we have UX prime and UY prime. So we specify these coefficients that you have in matrix 27 through real constants. And S1 bar, S11 bar, and S12 bar, and S22 bar I already showed you from the previous slide. So the bond connectivity are shown here. For example, this is an ANSYS screenshot, and network of elements are shown here. Bond breakage is achieved through the kill option. Coupling of peridynamic and Fe regions achieved through the coupled degrees of freedom command. As you can see here, I have this blue region is the finite element region, and this pink region is the peridynamic region. So what we have is these nodes, the yellow nodes, basically they are the coupled PDFE nodes. Okay, so in the pink region here, I have peridynamic interactions through the matrix 27 element. And in the blue region, I have traditional plane 182 elements. And on these yellow nodes, I specify this coupled degrees of freedom command. So I make sure that the displacement components in X direction and Y direction, they are the same as I come from the Phi region, as I come from the PD region. So now brings us to the kinetic theory of fracture. Basically, fracture is a thermally activated process. That's the main assumption. So it accounts for the effect of time and temperature. This theory was introduced by Coleman and Zhurkov in 1956 and 1965. So all atoms and molecules oscillate in accordance with Planck's law. Thermal energy is associated with each oscillation is not a single number, but a distribution. So here is the likelihood of transition. And we have bond breaking rate. This is KBIJ. You have the oscillation frequency. H is the Planck's constant. Your K is the Boltzmann constant. So T is the absolute temperature. In this expression here, the exponent of the exponential function is you have the activation volume gamma, you have the activation energy U, then we have the bond stress between I and J. So bond stress facilitates the bond breaking process by reducing the activation energy. Okay. So the damage variable evolution is through the state variable. We have this simple differential equation here, N, and we have the parameter lambda here, controls the shape of the damage evolution curve. And we substitute for bond breakage rate, KB, from the previous slide, and we can rewrite this. And N naught that you see here is determined through this constraint equation here. Okay, so if you integrate this equation, and that's the solution to that, simple ordinary differential equation here, and at any given time, for given initial value of that state variable N naught, we can integrate and determine the value of the state variable. If it was 0, it's undamaged. If the state variable is 1, it's failed. So once we integrate for a given specified specified number of load cycles, n star, and f is the frequency of loading. I have Ni is the initial value of the damage parameter at time Ti. So I have my maximum stress, the minimum stress, R is my load ratio. Then I can just explicitly write that expression down that I showed you from the previous slide in discrete form. So in order to gain computational efficiency, the maximum stress is approximated by applying a static load equivalent to the highest peak load in cyclic load. So details of this you can find in this paper, Yanan and Fertig 2017. So how do we determine the activation volume and the activation energy? It comes from the SN data. So we approximate the SN data with line segments corresponding to different stress state. And the slope of that line segment is going to give you the activation volume. Intercept is the activation energy. And this only represents the fatigue data. It's the strength data. So it's not, the fracture data is not reflected in this. So what we do is we calibrate the activation volume and the activation energy by bringing in the mode 1 fracture data. So here is the experimental curve, the blue dots. And so we calibrate, we change gamma and U so that we recover the experimental data, and we introduce these calibration parameters, R gamma and RU. So bond breakage is very straightforward. So if the damage variable is larger than 1, we break the bond and we put a cut at the center. And so damage state variable does not specify the direction of crack path. So therefore we use maximum stress criteria along with visibility. And so damage is defined as the ratio of broken bonds to the total number of bonds. And if the damage is about 0.5, then we say, okay, we have a crack surface there. In this figure here, what you see between point K and J, you have this red bond, which is a broken bond. Once we break this bond, then we introduce this dark or black dots, like that's the incremental crack. And the direction is based on the maximum stress criteria, but also on each side of this line, if the nodes are not visible to each other, we also break those bonds. That's the visibility criteria. And so the implementation is pretty straightforward. We apply the load, solve the peridynamic equilibrium equations, get the effective bond stress, and we determine sigma max, sigma min, and then we evaluate the damage accumulation value and K for each bond. If it's larger than 1, we break the bond. If not, we basically increment the load and then repeat this process. So I have two numerical results. One is mode 1 fatigue crack propagation. Here you can see we have the finite element region and the peridynamic region here. And the applied maximum load is 14,000 Newton. The frequency is 10 Hertz. Load ratio is 0.1. And so we apply this load. This is our peridynamic region. The grid spacing is 0.5 millimeter. Horizon size is 3 times the spacing. And so we have the activation energy, activation volume for different stress levels. And in this case, we have 5 different line segments. I have the activation volume, activation energy, activation volume here. And so we calibrate, right? So the crack length versus number of load cycles. So the calibration parameter is 2.6 and 1.04. And then I'm going to show you how fatigue crack propagates at different number of load cycles. So the after 3,000 cycles, crack growth initiates and starts propagating in a self-similar manner. And about 44,000 load cycles, it reaches its critical value and final failure occurs. Here is the crack length versus number of load cycles. So the prediction, peridynamics and kinetic theory of fracture prediction very nicely captures the experimental data. Then I move on to a mixed mode case where you have the compact tension test specimen. And the load mixed mode is dictated by this load angle alpha. It's going to be 30, 45, or 60 degrees. Again, we model this region away from the crack tip and crack with finite elements. And here's the peridynamic region. Everything else is the same in terms of grid spacing and the horizon size. And I'm going to show you some results for alpha being 30 degrees, crack length versus number of load cycles, and predictions compare well with the experimental measurements. And so prediction is 26.6 degrees, experiment is 31.7 degrees for crack initiation angle, and the crack length and number of load cycles very nicely match. And when I come to 45, I see a deviation here, which I will explain in the next slide. So predictions deviate from the experimental results after 25,000 load cycles, and initiation angle is 35.5, experimental we have 40.26. If I go to 60, again, predictions compare well with the experimental measurements. We have 45 degrees versus 51. The crack length versus number of low cycles very nicely agree. Now, look at this, crack length versus number of low cycles, 30 degrees, 45, 60 degrees. One thing that we know is that crack growth rate should decrease with increasing load angle. But what's happening here, as alpha is 30 to 60, clearly the crack growth rate is decreasing. But in the case of a 45, experimentally it is increasing. So this is unreasonable. So this is an unreasonable experimental measurement here. So we should be aware of that. And so as remarks, basically what I've shown you is a coupled PD-FE approach for simulating fatigue crack growth based on kinetic theory of fracture. We use matrix 27 element native to ANSYS for the stiffness matrix of peridynamic bonds. And failure criteria is based on the evolution of damage state variable in kinetic theory of fracture and visibility criteria. We successfully predict crack initiation, propagation path, and final fatigue life under mixed mode cyclic loading based on SN data and mode 1 fracture data. So with this, thank you so much. And if you want to learn more about this approach, there's a paper out in the Journal of Peridynamics and Non-Local Modeling. And if you have any questions, please feel free to ask me.